Hi, my name is Ira Globus-Harris, and I'll be presenting my work with Michael Kearns and Aaron Roth on algorithmic frameworks for bias bounties. His work was done at the University of Pennsylvania and during an internship with Amazon Web Services. Any views or opinions are my own. Machine learning models discriminate in undesirable ways, and the study of algorithmic fairness is one attempt to partially remedy these issues. However, the field has several challenges. First, fairness is generally stated as a constraint to an optimization problem, where fairness is positioned in direct tension to overall model accuracy. Thus, in order to make a model fair, some groups' error rates will be artificially inflated. Second, all downstream use cases need to be accounted for. The groups you want to be protected against must be known ahead of time and fully specified. Furthermore, your fairness guarantees are only with respect to your training distribution. In an era of machine learning as a service, this isn't particularly realistic. Finally, there are no good mechanisms to improve unfairness discovered after deployment. This makes relationships between auditors and organizations adversarial instead of one that rewards auditors for their efforts and which makes the models better. We'd like to have a form of algorithmic fairness that addresses these limitations. We do so by looking to the security community. We have designed bug bounties. These programs turn a potentially adversarial relationship between software developers and hackers into a mutually beneficial one. Developers post bounties for security bugs in their software and monetarily reward hackers who locate bugs. Here, we can imagine a similar bias bounties approach. External auditors are invited to find bias in a model. They send this information to the company and are rewarded for doing so. Then their discoveries are incorporated into the machine learning model to create a better and more just one. Such a model leads to natural questions. How should the bounty hunters describe the unfairness they discover? How do we evaluate these descriptions? How do we distinguish between a case where the bounty hunter is describing a group that our model is expected to perform poorly on, like the set of all very blurry images, versus one that represents real harms? How can we incorporate this new knowledge into our model without completely retraining? How do we prevent adversarial behavior by bounty hunters who, for example, might try to learn our validation method and overfit to it? Our work provides methods to tackle these questions. We require that bounty hunters submit GH pairs of group identification functions G and models H, such that the model H does better on points in G than our current model. We use holdout data to validate that this is in fact true, and then update our model to use the new model H whenever a point is in group G. In essence, these updates just form a decision list. After T rounds of updates, we have a decision list where point X will be classified according to the group that it is a member of. This has a nice property. Assuming that each update incurred a delta improvement over some mu density of your distribution, you will converge to close to the best possible model after 1/mu delta rounds of improvement. It also has a problem. If your groups overlap, which we know that they do in the case of demographic identifiers, you could have group errors increase rather than decrease over time. We don't want this to happen, so we test for these occurrences and modify our algorithm to incorporate repairs to the decision list whenever they occur. This final algorithm has the same convergence guarantees to the best model as before, but with the added benefit of monotonically decreasing errors for all groups over time.